Okay, so let us start with the Schrodinger's equation. So let us first understand what the Schrodinger's wave equation is. Let's start with a simple case. The total mechanical energy of a particle is given by the addition of its kinetic energy as well as its potential energy. Kinetic energy is K, potential energy is denoted by V, and E is the total energy. But in quantum mechanics, every observable quantity has its corresponding operator. So K must be replaced by K hat, V must be replaced by V hat, the potential energy operator, and E must be replaced by E hat, which is the total energy operator. So the question is, what will they operate on? Definitely, these operators will operate on psi. So we have K operating on psi, V operating on psi, and E operating on psi, where psi is a function of position and time. So for simplicity, we have considered the position to be x, y, and z in Cartesian coordinates and time to be t. So now putting all the values, we know from the previous class that the kinetic energy operator is given by minus h cut square by 2m, this operator, Laplacian operator, psi, and V operator is, the potential energy operator is kept as it is, V hat. The total energy operator is IH cross d by dt, again from our previous classes. So if I write down explicitly the Laplacian, this is what we get. The Laplacian is del square del x square plus del square del y square plus del square del z square acting on psi plus V psi on this. So this is, let us say, our equation 1, and this equation is basically called the Schrodinger's wave equation. Let us understand what it says. In Newtonian mechanics, if you push an object with a force F, let us say in this case for simplicity, it moves in one direction, then the equation governing that motion is Newton's laws of motion, or Newton's second law, that is F is equals to ma. But in this case, the acceleration is del square x by del t square. This is a differential equation, or a second order differential equation, and by solving this differential equation, we get the position of this object, let us say this block, the position which is changing with respect to time, the velocity which is changing with respect to time, the energies, every observable quantity we can get which is changing with time. And we know from classical mechanics that all these observables actually exist in classical mechanics. They do exist even if we do not make an observation. So this Newton's second law of motion is basically what we solve to find out all the observable quantities given a force. The corresponding equation in quantum mechanics is the Schrodinger's wave equation. Remember, we do not have well-defined observables in case of quantum mechanics. What we have for a particle is its wave function psi. So all the information that we have, all the information of the particle is stored in the wave function psi. And this equation, the Schrodinger's wave equation, governs how the wave function evolves with time or how the wave function changes with space. Look at the left hand side. This tells us how the wave function changes with space. And this right hand side tells us how the wave function changes with time. So say for example, if I take a particle, let's say, and it is defined by a wave function like this, and we are observing this wave function at a particular instant. So this is basically a snapshot. So if you take a camera and take a picture, this is what you would expect for the particle. This wave is nothing but What this wave is telling us is this probability, the probabilities of finding the particle at different location in space. Just for example, consider only one dimension, x. So this variation in psi, so we can see that psi clearly changes with the position. So what this left hand side tells us is how the wave function psi changes with position. That is, if we move along the x-axis, what are the various probabilities or the likelihoods of finding the particle and how it changes, how psi changes with position is given by the left hand side of the equation. And let us say now, if this particle moves, like this block is moving, if this particle moves, this wave function also changes with time. Let's say this is a snapshot at t equal to 0 seconds. In the very next instant, and at t equal to 0 seconds, the probability of finding the particle is maximum at this point of space. You can see this from the wave function. As the particle moves through space, this wave function also moves with the particle. So the very next moment, let's say the particle has moved to this spot, then the probability wave function might look like this. So here, the probability of finding the particle at the very next moment, let us say t equal to 1 seconds, the very next moment, the probability of finding the particle over here is 0 because the particle has moved over here. So the probability or the most likely position where the particle is to be found is over here. It can also be found over here with a lesser probability. Again, it can be found over here with a lesser probability. But we can see that the wave function moves through time. So this right hand side tells us, how the wave function changes with time. So we can see this animation. You can see it's the spread of the wave function. This is the spread of the wave function. This is what it says, how it changes with space, the left hand side. And since the particle is moving, we can see the wave function is also changing with time. This is what the right hand side is telling us. So like we have in classical mechanics, the Newton's laws of motion, in quantum mechanics, we have the Schrodinger's wave equation, which tells us how the wave function of the particle, which contains all the information about the particle, changes with space and with time. So let us solve this equation. Let me erase this a bit. So let us solve this equation using a method called separation of variables. So we know psi is a function of x, y, z and t. Let us take it as a product of two functions. One is eta, which is a function of position only, and the other is phi, which is a function of time only. And let us put this eta into phi, which is psi, in this equation 1. Since phi is a function of t, and here we have differentiations with respect to space, phi can be taken out. So phi is out. The differentiation is only for the function eta. Plus v psi. Psi is replaced by eta into phi. So we have eta into phi. And here again, this is with differentiation with respect to time. So since this is a function of position only, eta can be taken out. So it is d phi by dt. Now dividing this equation throughout by eta phi, we get eta here, because if we divide it by eta phi, phi gets cancelled. We have an eta over here. We have a v operator. And again, if we divide the right hand side by eta phi, eta gets cancelled, and what we have is just a phi. So this is our equation 3, and if we look at the equation 3, the main assumption is, let us assume that the potential energy is a function of position only. The potential energy, in other words, the potential energy does not change with time. So let us say we have a system. In many cases we do have it, that the potential energy do not change with time. It does not change with time. It is only a function of position. So for example, we have two charged particles, plus q and minus q. These two have a potential energy in between them, and the potential energy only depends on the distance between them. That is, it is a function of, the potential energy is just a function of position, r, let us say. It doesn't depend on time. So we do have situations in physics where the potential energy does not depend on time, and let us assume that fact, that the potential energy does not depend on time, which implies that the right hand side, or sorry, the left hand side is just a function of position, and the right hand side is just a position of time. So we have decoupled the equation. Equation 1 was a coupled differential equation where psi was a function of both position and time. By separation of variables, that is by taking psi as product of two functions, one function of space and one function of time, we have managed to decouple the differential equation. One differential equation on the left is a function of position only, and the other on the right is a function of time only. So we have managed to decouple the equation, the coupled equation. So let us see. This is what I've said. If the potential energy is a function of space only, which is given by this, no time function, the left hand side of the equation 3 is a function of position only, and the right hand side is a function of time only. Thus, when we say that the left hand side is a function of position only, that is, the left hand side gives us how psi changes with position, and the right hand side tells us how psi changes with time. They are completely independent, and still they are equal at any case, which implies that they are individually equal to a constant which neither depends on space nor depends on time. So we put the left hand side, see, this is our left hand side of the Schrodinger's equation, and we put it equal to a constant E, where E is the total energy of the system. Now, multiplying throughout by eta, what we get is this. We can see this equation is just a function of position and tells us how eta, which is a part of psi, remember, psi was equal to the product of eta and phi. So this equation tells us how eta varies with space. So if we are able to solve this differential equation, we will be able to solve for eta. And this is called the time-independent Schrodinger's equation. Similarly, if we put the right-hand side equal to E, this was our right-hand side, and if we put it equal to E, this is what we get. Again, this is a differential equation, and by solving it, we get phi. This is called the time-dependent Schrodinger's equation. So by solving equation 4 and 5, which are the time-independent Schrodinger equation and the time-dependent Schrodinger equation, we get eta by solving this, and we get phi by solving this. And if we multiply the two, we get the final wave function of the particle. So let us solve 5 first, because we can see that this is more complex, the time independent one, because it's a second order differential equation. We need to solve the second order differential equation to find out eta, and this is a first order differential equation to solve phi. So let us solve equation 5 first. So the solution of time dependent Schrodinger's equation. This is our time dependent Schrodinger's equation. I h cross d phi by dt is equals to E phi. So just by reshuffling, if we take phi down, we have d phi by phi is equals to E dt, we take dt here, divided by I h cross. And if we take the imaginary iota to the numerator, we do have to put a minus sign. So minus I e by h cross dt. This is equation 6. And if we integrate it once, we get, this is the equation that we need to integrate. We get ln phi is equals to minus I et by h cross plus ln c, where c is the constant of integration, which we can find by the initial condition, that is t equal to 0. So by taking the exponent on both sides of the equation, if I take exponent on both sides of the equation, what we have is phi t, this is what we get, is c e to the power of minus et by h cross. This is the solution of time dependent Schrodinger's wave equation. See, we have found out phi. So this is the solution of time dependent Schrodinger's equation. Thank you.